Now we are connected to Dr. Payam Mershahi from the University of Cambridge. First, I will present you, then we will ready to listen you. Is it okay?
Sounds good.
Okay. Payam Mershahi received his undergraduate degree in plant biotechnology from the University of Nottingham with an intercalated year at Syngenta and the John Innes Centre, Norwich. Payam's PhD and postdoctoral research concerned biosynthesis, compartmentalizations, and mechanism of transport of vitamins in photosynthetic organisms. At the University of Cambridge, he is both a senior research associate and manager of the Algal Innovation Center. By using synthetic biology principles, Payam has engineered microalgae to produce valuable chemicals and subsequently scaled cultivation of the engineering strains in the IAC. Payam's other research interests concern the application of microalgae in remediation of food wastes. Okay, we are ready to listen you.
Okay, wonderful. Well, I want to thank the organizers for this nice introduction, but also particularly for Bharat for the invitation to speak at this conference. It's really unfortunate that I can't be there with you. My flight was cancelled last minute on Wednesday morning because of weather issues. And I was really looking forward to being there in Istanbul to see the various facilities and to be able to interact with all of you. But I guess that'll have to wait until the next time. Today I'm going to introduce to you what we do here at the Algal Innovation Center, which is located within the University of Cambridge. Professor Alison Smith spoke yesterday about research in her group and how we are utilizing synthetic biology, for example, approaches to engineer microalgae. And she alluded to the fact that we are looking at using the Algal Innovation Center for scale-up of our activities. And so I'll explain a little bit about how we endeavor to do that. I want to start by saying that as Vitor and others throughout this conference have nicely captured in their various talks, we're living at a really exciting time when it comes to algae.
Dr. Payam, I'm really sorry. We couldn't see your slide. Did you share with us, or we couldn't see it?
Yes, I am sharing. I'm sharing my screen. Is it not showing?
No, we can see it.
Okay, let me try again.
1 second. We can still see it.
You still can't see it?
Yeah, unfortunately.
Apologies for that. Share?
Yeah, we can see it.
Okay. Is it in PowerPoint mode?
Yeah, we can see it clearly now. Okay, thank you.
Wonderful. Well, apologies for the technical issues. I hope you can still hear me and you can see my slides now. As I was saying, I think it's an exciting time to be working in this sector. This is a figure from now 2021 from this paper by Arayo et al. Who showed, the numbers we can argue over, and Vitor again has probably the most up-to-date figures in his slides. But the general principle is the same, that the number of new companies operating in this sector in Europe has been increasing. They increase depending on various economic conditions that the sector faces, say the fuel price crisis through the decades. But ultimately, when you look at the blue line, which is the number of total companies operating in this sector, it's been on the rise, and that's really exciting to see. And it poses new challenges. So this number is increasing ever more, and not just because of fuel costs, but also because of interest in the various applications of microalgae. And again, Vitor and others have highlighted how industry and academia are looking at algae and their applications in various processes. And that's really what's to be excited about. Now, the challenges that come with this mean that translating what we are able to do with algae in small scale or in the lab to actual scales that are meaningful and can have impact in the outside world is a whole different ballgame, and it's a challenge to be reckoned. I really like this statement on Corbium's website that suggests scale-up is challenging, and it will be more challenging if it's adaptable. So as academics, as researchers, we need to engage with the scale-up technologies. And again, it's fantastic to be in this time slot because of the previous speakers that came along and beautifully explained the challenges and opportunities that exist when we work with engineers to look at opportunities to scale up cultivation of algae. So it's time-consuming, it's costly, but the later you leave the whole process of engaging with the scale-up process, the more issues can arise. So that was the mindset that helped us build and set up the Algal Innovation Center. For those of you who have not been to Cambridge, the work, our algae research, the core work that's done in the lab takes place in the Department of Plant Sciences, which is in the center of the city, center of Cambridge. It's been there for quite some time, 1904 until now, and the Algal Innovation Center was built as a result of the research from this, the labs in this department. So the fundamental research that took place meant that now we had evidence that we could do various things that are exciting and can be used for various applications, but we needed to go beyond the lab. And in 2016, we built this facility in the Botanic Garden of the university, where we have now the capacity to do just that, to test pipelines for algal-based solutions. Now, we had an actual space that we could take all of the work that Alison talked about. So, for example, the symbiosis between algae and bacteria, the synthetic biology-driven approaches for engineering microalgae to produce high-value compounds, and then the metabolic analytics that can be applied to algae to understand how their pathways work, how they work with each other, how they are affected by the environmental conditions or conditions in general that the algae are grown in. When the Algal Innovation Center is really at its fullest, this is what the inside of it looks like. So we have the capacity to grow different types of algae from Phaeodactylum, chlorella, Chlamydomonas, in different types of bioreactors. We've got incubators to use, but also hanging bags. We've got the Varicomacro phycolith. Marco speaking after me, this I think came from his PhD work. Then we've got the horizontal reactors, we've got harvesters. So we can go through the whole pipeline from shaking flasks all the way to the different types of bioreactors that help us to evaluate algae and its performance at different scales. In terms of our current focus, we are based at a university, so education is one of our core interests, and then there is research and contract research that we engage in. So first on the list of our activities is optimization of cultivation and processing pipelines. So taking, for example, we can transform algae in the lab, and you can see some of the colonies of transformers here on the Petri dishes in the image at the top. Then we can take those colonies and evaluate them for their performance. Olaf nicely described the issues that one needs to be mindful of. So transgene stability of expression. Then there is the production capabilities of your strains, identifying strains that are able to produce the highest amount of your compound of interest, for example. And we can determine that in the lab, and then subsequently we can start to ask, well, how do those strains behave and perform when they're scaled in a natural environment in the Algal Innovation Center. We can perform analytical profiling, strain improvement and evolution studies. We can do molecular analysis of algae and culture microbiomes, so flow cytometry is something that we rely on to look at population dynamics between the bacteria and the algae. We are engaging with life cycle analysis and techno-economic analysis of our systems on site. We have the capability for NGS, so Oxford Nanopore type sequencing, and we've got appropriate bioinformatics pipelines in place to understand what are the classes of organisms that exist in our cultures. And, as I said, education is a major part of our endeavors, our interests, and we run algae biology and biotechnology training courses at the university, and that's really important for us. It's really important, we believe, for the sector, because as we start to look beyond the lab, there are a series of other technical know-how that individuals from the biology angle, but also engineers need to start to be mindful of, be aware of, and we need to engage with each other in a hands-on approach. So this is something that I'll touch on later in my talk, but the picture here is Berat and colleagues from Istanbul who came to this particular workshop that we were running in the Department of Plant Sciences at Cambridge. This is one of our final in-person events before the COVID pandemic hit. So here we are. This is a map of the UK. This is the outside of the Algo Innovation Centre. And you can see Cambridge in orange, and we're located here. What I've done in this map is highlight academic institutes or institutes in general that are involved in algae research in the UK. So all of these flags are those that are operating actively in algae research. And in the lighter orange or yellow color, I've highlighted all the institutes that have got some form of scale-up facility. So that could be just having your 10-liter PBRs or 5-liter PBRs, but any means of being able to scale up algae cultivation. The reason why I wanted to look at how the spread of access to scale-up facilities right now, what's the current status of that in the UK, is because it's really important that academics working in our sector are able to look beyond the lab, to have access to these facilities where they can test how their strains perform at scale, and work with engineers, work with individuals who have the know-how to scale up their strains of interest, and to feed back the information that they require to go back to the lab and test certain restraints that are placed on the algae when it's scaled up. So access to these sites is important, and as a sector, we need to encourage their development. I'm not just saying that because I manage the Algo Innovation Center, but as a sector, we need to be encouraging the development of these sites and interaction between sites, and that's something that's near and dear to my heart, and I want to encourage everyone to engage. In terms of optimization of cultivation and process and pipeline development, I want to touch on that. We are really trying to take a similar approach as we take in the lab, which is taking a design, build, test, learn approach. This is a typical synthetic biology-driven principled approach that you take to systematically test how you can build the best system for producing, say, a compound of interest. So initially, you start by your design step. So this is in silico testing, identifying, defining your problem, designing your experiment, and modeling, and ultimately arriving at what are the components that need to be put together to achieve the best output. And then building those parts, or putting those units of DNA together, transforming your algae, and then asking how is the performance of that algae. So again, Olaf describe the screening procedures, the various steps that one needs to take in order to be able to identify a strain of interest. And then as a result of the experiments done, you learn and you can go through the whole cycle again. We've decided to take a similar approach during our scale-up pipeline. We think it's important to be principled in a similar way, because then there's a case of being able to compare our work and compare our output with that which is done in the lab, and be able to feed back our information and know-how back to the lab so that the strains can be further developed or conditions can be tested in a controlled manner, and then the information from that be fed back to scale-up facilities like the Algo Innovation Center. So briefly, to remind everybody, we are interested in Chlamydomonas reinhardtii and Pseudoxylon trichognathum. And these model organisms are fantastic for engineering because the tools are available. Again, I think others before me described how important it is to have the necessary tools to achieve certain milestones in terms of expression of genes of interest, for example. Once we have our system and we've defined what was our host, we are able to put together pieces of DNA. So for example, in this case, caspin synthase, which is required for generating this diterpenoid caspin. So this is work that I was involved in when I first arrived in Cambridge to get Clammy to produce this particular compound, and this had interest from the pharmaceutical sector. Funding came from pharmaceutical sector to see how a photosynthetic organism, namely algae, could produce this particular compound. And we were successful in generating these strains, and these are actually what we are using in our scale-up facility at the moment. The student's name, Antran, indicated here, is the one whose PhD was all about taking these strains and testing their capabilities in the Algal Innovation Center. So she really took them through their paces. She applied a different scale up in the Algal Innovation Center, from the flasks to bags to the different bioreactors, applied microscopy, tested various parameters, cell OD to flow cytometry, etc. And the nutritional profile of the media, the algae itself, of course, Cas-Bean analysis, and was able to learn what are the conditions that lead to reduction in production, it impacted the health of the cells, impacted the size of the cells, and we could take this information and now isolate some of these particular parameters in the lab and ask, if we hold everything else constant, what is the specific impact of, say, temperature or media or specific molecular regulatory networks that impact production of your compound of interest? And we're finding very interesting data, and that's work that, so Anne's defending her thesis next month, and publications from her thesis will be coming out soon, so I guess watch out for that. We take common objectives for our AIC project. So establish a workflow for scale-up. We test various abiotic parameters at scale, and then it's the biotic factors that also play a role, so characterizing the microbial communities, for example, and then we take our data back to the lab and test those specific parameters as I just mentioned. We see various challenges. When everything is working, everything looks beautiful and wonderfully is growing. But actually, crashes happen, and we all have suffered from crashing of our cultures. It's painful, but actually what we decided to do from the outset was, through constant measurement of various parameters, we were expecting and looking for instances of crashes and trying to link particular parameters and changes in those parameters with the onset of our crash. And we think it's important to have that data set, because then we start to learn about what are the conditions that lead up to crashing of our culture. It's not always just the presence of a bacteria in your culture. In fact, what we're seeing is bacteria, ciliates, and algae can sometimes work together. We've had cases where our friendly ciliates were there to eat up the bacteria, which then allowed our algae to flourish. So it's not always a case of trying to diminish the presence of other organisms in your culture. It's trying to understand the system to try to optimize the condition. Moving on from this, sorry, I'm just going to hide this panel. We are also interested in the role of algae in circular bioeconomy, and again, many have spoken about the uses of algae in remediating waste. This is an area of interest for us as well. We want to learn how we can take crop or fruit and vegetable waste, organic waste, anaerobically digest it, producing biogas and digestate that is often used for fertilizing land for crop production. We know that we can use it as a fertilizer to produce algae. And we've been working with various partners in different countries, particularly in Uganda and Ghana, to test if this can be a solution for market-side waste, for example. That is a major issue for our partners in those specific countries. We've worked with them to generate anaerobic digestion facilities and know-how to learn how to grow algae on the digestate, and then what to do with that biomass, what can be done with that biomass, and what are the properties of that biomass. And indeed, next month, we're going to Makerere University to build our first algae cultivation unit, where they can actually then link up their anaerobic digestion facility with algae cultivation. And we're running workshops to train the workforce that can actually operate and operate those particular units in Uganda. What we found through that work is that there's some interesting properties that one could obtain from growing algae on anaerobic digestate. So Alison mentioned about vitamin B12 and its production by bacteria. Well, that's definitely what's happening in anaerobic digestion process. The bacteria in anaerobic digesters are producing boatload of vitamin B12. And what we found is that vitamin B12 can be accumulated, it can be taken up by chlorella, and that can enrich that chlorella, which normally does not make any vitamin B12 and relies on the environmental sourcing of vitamin B12. And as we know, chlorella vulgaris is one of the key supplements that is trying to address deficiencies in certain subset of population. It's very popular with vegans and vegetarians who may be low in vitamin B12. Knowing that, of course, chlorella vulgaris grown on anaerobic digestion is never going to end up in supplements, but knowing what types of vitamin B12 can be taken up by chlorella vulgaris as part of this work has been very helpful for various different end applications. Just to share some data with you, we were able to grow chlorella on AD and on various other control media, and we show that growing chlorella on AD does not lead to changes in protein, carbohydrates, or lipid content of the alga, but that growing it on AD does result in, so this is vitamin B12, a microgram per liter. So when grown in control media, again, under non-axenic condition and non-sterile conditions, where there is some bacteria in your control media, there's a little bit of vitamin B12 from the bacteria that inoculates that media. This is TAP. But when we use AD, so only AD as our fertilizer for growing algae, our cells are able to accumulate vitamin B12 to quite high levels. So 27 microgram per gram of vitamin B12 being accumulated in the algae. And the rest of it is extracellular. This means that now our cells have reached capacity for accumulation of vitamin B12. The rest of the vitamin B12 that's in the media, from the AD, is present and can be further utilized through top culturing processes. So this is what we've shown. Our fruit and vegetable waste is very low, or almost it has no vitamin B12. Then through anaerobic digestion, you accumulate vitamin B12 in this biomass, and then subsequently, when you grow chlorella on the anaerobic digester, you can further bioaccumulate vitamin B12. This work should be coming out soon. We're wrapping up the paper to submit, and so I'll encourage you to look out for that. We work with academia and industry on various different projects, and so I mentioned one part of our project on waste remediation. We're also interested in fortifying of bivalves with micronutrients using microalgae. So this is with David Aldridge at the Department of Zoology, or enhancing nutritional profile of black soldier fly larvae. And so this is looking at whether it's possible to enhance the nutritional profile of this particular insect, which is very popular in consuming fruit and vegetable waste, or food waste in general. But one of the issues that this particular company that approached us were facing was that because of the nutritional qualities of the particular food source that they were giving their insects, their fecundity was lowered, so they were not able to reproduce as well. So over generations, the health of the larvae deteriorated. They asked us if we were able to provide algae and help them with a setup of feeding trials to see if actually supplementing their diet with a low amount of algae would help that. And what we were able to do is work with them on these feeding trials, and we took the trial over and it did a trial and error to see how much algae you could actually incorporate into the biomass, into the feedstock. So too much of algae, and you have too wet a food source for the larvae. But essentially what ultimately we were able to do is that through these feed trials we could show that adding algae did not impact negatively or positively the protein content, the vitamin content, the fatty acid content of the larvae. In terms of the reproduction qualities of the larvae, which is the main interest of the company that approached us, these are ongoing trials, so we're waiting to see how this plays out over a time course. So as I said, we work with different industries, and that's been the remit of Algal Innovation Center, to work with industry to test different kits that they develop and see where their limitations and opportunities lie. And at that point, I'm going to pivot towards our education front, because working with those companies has highlighted that there is a huge demand in terms of skill sets that individuals entering the industrial settings require. And that can only come through going beyond the academic world and really getting your hands dirty and understanding the challenges that the sector faces. And this is the kind of baseline for why we started to think about needing to put together a course like this, Algae Biotechnology Techniques and Opportunities for the Sustainable Bioeconomy. Some of you have been participants on this course. It's been running since 2018. We've had over 350 participants. It's quite popular. We are always oversubscribed. It used to be a 2 or 3 day in-person course where we would hold the meeting at Mattis in Iceland, Fraunhofer in Germany, or Department of Plant Sciences here in Cambridge. Subsequently, we started to expand. Now the course also involves Oben in Sams, as well as we ran one course at A4F in Lisbon. This is all halted because of the pandemic, and so we've gone online. So this is one of the in-person cohorts that came to Cambridge. Subsequently, we've had speakers, some of whom are listed here, and you can see Berat on the list here, of course. It's been fantastic to have him both as a participant and subsequently as one of our expert speakers who's been coming on and sharing their experiences of how the sector is evolving and the kind of technologies that are available for the sector. This is Ben-Hang Premier talking in December about potential of algae in the global market, and that was a really interesting talk to hear as well. So we're securing this course for the 2023 to 2025, and we're redesigning it so that it is actually an accredited course that can then be helpful for professional development of individuals working in the industrial setting. We are always interested in keeping our costs down, so we've got a tiered cost model where students pay minimal fees, and we are also looking to reinstigate the in-person courses. So watch out for those areas. And another course that we are also involved in is this Sustainable Aquaculture Inspire Autumn School. So this is, again, with various colleagues from across across Europe, I guess, Iceland, Poland, Scotland, and Northern Ireland. And here we're looking at an entrepreneurial spine to the program. So we're combining it's not just microalgae, it's looking at hatcheries and how microalgae can be involved in that, and opportunities for business startups to operate in this sector. With that, I'm really at the end of my talk, and I hope I've given you an impression of what we're about, what we do, and what our expertise are. And I want to thank various individuals that have helped the Algal Innovation Center and are involved. And it's one thing to grow them in the lab and achieve a very high level of productivity, but Olaf really pointed to an important issue that we face, which is when you start to scale up, some of the conditions of, for example, the overlay that you apply to your algae is just not possible in a scale-up facility. And so what we've learned is that you need to start to look beyond the conditions that you set up in the lab. And it's really, we haven't got the answer for all of, well, we don't have all of the answers for sure, and for how you can grow algae at scale in the best way possible. What we do well, and what we're doing constantly, is collecting information, making sure that we're collecting parameters in a systematic way, so that once we start to do an experiment in the Algal Innovation Center with our GM algae, be it Chlamydomonas or Pheodactylum or Cholera, we are capturing the same rigor of data, and we can learn from that. So mass data that we've accumulated we're trying to then understand what are specific conditions that are leading to certain pathways being overexpressed, how those pathways are interacting with each other, what are the conditions that are leading to, for example, stresses on the cells that subsequently reduce our production capabilities. And again, we talked about those algae-bacterial interactions, so we're definitely interested in seeing how exchanges between bacteria and algae impact your ultimate culture productivity.
Thank you so much, Payam. Thank you.
Do we have more questions? Okay, no. Again, thank you, Dr. Payam, for your presentation, and take care of yourself.
Thank you, and you all too.
Bye.